Welcome everyone. Today we'll discuss some of the problems related to acid-base biochemistry, biochemical thermodynamics, and stabilizing interactions in biomolecules. These questions will help you in better understanding of the concept related to these topics. So let's start. If we look at the first question, it has been asked, it's a multiple choice question where it has been asked, choose the possible option showing a strength of stabilizing forces or interactions. So they have given different kind of stabilizing interactions. Few of them are non-covalent interactions. One of them is ionic interactions, and they have asked the strength of stabilizing force interactions. So if you look, you might be aware with the electrostatic potential energy for these charges, be it for these interactions rather, be it ionic, be it ion dipole, dipole induced dipole, or dispersive forces. So the general formula is Q1, Q2, where these are the point charges. You have Coulomb's constant, which is denoted by K, which is equal to 1 by 4 pi epsilon 0. So EC, electrostatic potential energy, is equal to K Q1 Q2 by epsilon R into R, distance between them. Epsilon is the dielectric constant. So this is the general formula for the 2-point charges, which I'm talking about, the electrostatic or the ion-ion interactions. Now look at the relationship between this energy and the distance. Now if we'll go ahead, if we'll try to calculate these energy for these different interactions like ion dipole, 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 or the dipole induced dipole, you'll find a relation, which is of course going to be the inverse relationship between the distance, and we'll just have a look. So if I have to talk about ion-ion, the relation is, as you can see it from the formula, is 1 by R. We have ion dipole, and how the energy is related with the distance, it's 1 by R square. I hope you all are familiar. Then we have something called dipole-dipole, which is 1 by R cube, the relationship I'm talking about. Then you have dipole-induced dipole, where energy is related to distance between the 2 point charges as 1 by R raised to the power 4. And then you have the weakest force, which is dispersive forces or the van der Waals forces, which is represented by, where the energy is related to the distance as 1 by R raised to the power 6. Are you all able to see some trend? So by looking at these distances, I can tell you that if I have to compare the strength of the stabilization, I can say that ion-ion more stronger than ion dipole, which is more stronger than the dipole-dipole, which in turn is more stronger than the dipole-induced dipole, and the weakest interactions are the van der Waals forces or the dispersive forces, which are also known as the London forces. So if I have to look at these trend, I mean, this seems to be right. How about here? This again seems to be right. If I have to compare like the hydrogen bonding between the ion-ion and the London forces, remember hydrogen bonding are comparatively stronger than the London forces, but they are weaker than the ion-ion. So again, this trend seems to be all right. So the correct answer is going to be all of the above. Now read this question. Question 2 very carefully. A pharmaceutical molecule with antifungal properties is only active when deprotonated. So it's given in the question that when it's deprotonated, it's an active, and negatively charged. So that means if it's a deprotonated and negatively charged, it's an active molecule. The protonated state is inactive, given in the question. So if the pK of this drug is 10, calculate the ratio of protonated to deprotonated compound at the physiological pH. Simple. If they have given about, if they are asking about the ratio of the deprotonated and protonated with the pH value given, pK value given, I just need to use the simple buffer formula, the famous formula, which is Henderson-hasselbalch equation, where the pH is equal to pKa plus log base by acid. Now, if I have to solve the A part, the pH is given, which is 7.4. pK is given for this drug, 10 plus log. Now, base by acid, what is the base going to be here? With all these information, the base is going to be here is in the form of A minus, which is the deprotonated, and acid is going to be in the form of HA. So I can calculate, you can use a simple calculator to calculate these values. So this is going to be minus 2.6 plus log base by acid. Then you can take the antilog of this minus 2.6, and that will give you the ratio of base by acid. So it's coming out to be 2.512 into 10 raised to the power minus 3 ratio of base by acid. Now, if you look at the question, they have asked calculate the ratio of protonated to deprotonated. So I have to interchange it. I have to inverse it. So they have asked the ratio of protonated, that means HA by A minus. So what I need to do, 1 by 2.512 into 10 raised to the power minus 3 equal to HA by A minus, because this is what they have asked, and accordingly I have to choose the correct option. So if we'll try to solve it, you will get it a value which is close to 398. So I'm talking about this ratio of protonated to deprotonated, protonated to deprotonated. The ratio is going to be 398. So which are the options where we can see 398? This one and this one. Now the next question, B, is this drug likely to be a useful pharmaceutical agent? Now they have, I mean, it's given in the question, it's the deprotonated form, it's a negatively charged form, which is active. Now look at the ratio. If I can see the ratio, the protonated form is much more compared to the deprotonated form. So at this particular pH, where the pK is 10, the ratio is coming out to be, the ratio is coming out to be 398, which is quite big for the protonated one. If we look at the value of the deprotonated form or the negatively charged form, it's very low. So what can I say? Is this drug likely to be a useful pharmaceutical agent at this particular pH? No. So the correct answer is going to be 398 and no. Just have a look at this ratio. If I have to calculate the A minus, what is the A minus going to be? It's going to be 1 by 399, which is, if you look at this value, this is going to be very less, close to 2.50 into 10 raised to the power minus 3. So if there are very less molecules of the deprotonated form and negatively charged, which is said in the question is the one which is carrying the antifungal properties, this drug is not going to be useful as a pharmaceutical agent, because it's going to be remain in the protonated form at that particular pH value. Third question, which one of the following statement is true? The first one is dipole-induced dipole interactions could be attractive or repulsive. Remember, if I'm talking about the dipole-induced dipole, I need to have the dipole. Let's consider a dipole HCl coming in close contact with a non-polar molecule. Let's consider argon. Now, what I'm saying, this HCl, because of this electronegativity difference, has a dipole. It will induce a dipole in a nearby non-polar molecule. And how? By pushing the electrons. So if you can see, even though it's an ionic bond, they are going to carry partial negative charges, this one partial positive charges. And if this molecule is going to come in contact with the argon, at some point, because of this dipole, such dipole, you'll find uneven distribution of, like, this situation is leading to the generation of uneven distribution of electrons in the argon. So for a brief period of time, you can find all of the electrons coming together on this end, generating a partial positive charges and partial negative charges. Coming back to the option, dipole-induced dipole could be attractive or repulsive. It's going to be attractive. It's going to be attractive, not repulsive. So as you all can see here, it's pushing up the electrons on that side. And why that is happening? Because this end of this HCl molecule is carrying a partial negative charge. When it is going to come into close contact with the argon, where the electrons are moving in a so-called spherical manner, at some time point, this end will push the electrons to the another end of the argon molecule. I'm talking about the electrons of the argon. By doing so, they are going to they are going to induce a dipole. So which one of the following statement is true? No, this is false. Dispersive interactions, which are van der Waals or the London forces, are always attractive and can occur between non-polar molecules. Seems true. Like, these are always attractive. It's also called as induced dipole, instantaneous dipole, induced dipole. So there are non-polar molecules, as I said, for a brief period of time. Even though those are the non-polar molecules, they can, because of the uneven distribution of the electrons or the uneven movement of the electrons for a brief period of time, they can instantaneously create a dipole in one of the molecule, which is subsequently going to induce a dipole in the other nearby molecules. And why this is happening? Because of the nature of the molecule, and also remember, like, even we keep on saying the thing that the electrons are moving, they are moving in a spherical fashion. At some point, even for the non-polar molecule, you can find that for a momentarily the molecule is going to be polar because of the generation of these charges. So what I'm trying to say, let's consider you have the helium, 2 helium molecule, non-polar, with the electrons are moving at a certain brief period of time. The electrons can get pushed towards one of the end, generating negatively charged at this end, positively charged at this end. Now this will, so instantaneous dipole has been created. And it's quite simple. Like, these things keep on happening even in case of the non-polar molecules. Now, once the dipole has been created, it will induce a dipole in the another nearby helium molecule. Because if this end will come into close contact with a non-polar helium, they will push the electrons from this side to that side. By doing so, this end will become negatively charged, partial negative charge. This will become partial positive charge, and then you'll find attractive interactions between these molecules. So seems all right. Hydrogen bond is an acid-base reaction where the proton is fully transferred from donor to acceptor. False. It's written fully transferred. Always remember, hydrogen bond is not a real bond. You need to have a hydrogen bond donor, and then you have going to have acceptor. So it's a bond, which is not actually a bond. It's this hydrogen is getting shared between the donor as well as the acceptor. So it's not a complete transfer. So this is going to be false. The hydrogen bonds in anti-parallel beta sheets are non-linear. So if you all can recall the anti-parallel beta sheet where the two strands are lying in an opposite direction, what does that mean? The N end of one of the strand is lying opposite to the C end of the other strand. Same here, the C end is lying opposite to the N end. So the hydrogen bonds in anti-parallel beta sheets are non-linear. No, these are going to be linear. The most stable form where the hydrogen bonds are going to be linear, while the hydrogen bonds in parallel beta sheets are linear. It's a false. So in case of the parallel, where the two strands are lying in the same direction, and when I'm saying and, the amino end, when I'm seeing the carboxyl end, what would you find here? That here the hydrogen bonds are not linear, but rather non-linear. So again, both the two parts are wrong. So overall, this statement is going to be false. Salt bridge interaction is a combination of electrostatic interactions and dipole interactions. A very important interaction in the stability of the three-dimensional state of a protein molecule. It's a combination of electrostatic interactions, true, but not dipole-dipole. It's a combination of electrostatic interactions and hydrogen bond. So the correct option is going to be, which is the true, the second one. Simple question, the electrostatic energy between two oppositely charged ions placed at 1 nanometer apart in water will be, the values are given, what is the value going to be, and it's a negative marking, so you need to be a bit careful, but it's a simple thing. 2-point charges. I think the two options are getting repeated. One should be plus, one should be minus. If I am right, anyways, we will solve this problem. So Q1, Q2, K, epsilon R into R are given. So Q1, Q2 given, it's a point charges 1.6 into 10 raised to minus 19 coulomb. You can square it. Since they are given oppositely charged, it should be negative, plus and minus. Then K, Coulomb's constant value, universal. I mean, it's a constant whose value is 9 into 10 raised to power 9 with a SI unit. And then epsilon given for the dielectric constant of water 80. What else is given? They are placed 1 nanometer per hour. That means 1 into 10 raised to power minus 9 meter. If you'll try to solve it, you will get 2.88 into 10 raised to power minus 21. Rather, it should be negative because these are two oppositely charged ions. If they would have been the same charge, it could have been positive or negative. But here, if they have written oppositely, it's going to be minus. Now, what is the correct option going to be? I think there is some problem with these options. So you can either choose 2 or 4. Not 4 because it's in kilocalories. So this is wrong. Again, this one is wrong, kilocalorie. So we are left with this one, and the correct is going to be 2.88 into 10 raised to the power minus 21. As I said, it should be rather minus, but anyways, this is the one which is more close. It's not going to be kilocalorie. Why? We all know that 1 calorie equal to 4.186 joules. So you can all do those conversions and will realize that this is the best possible option, which is the second one. Next question. Biochemical reaction is non-spontaneous at all temperature when delta H and delta S is so simple. We need to use the Gibbs free energy equation, which is delta G equal to delta H minus T delta S. And what they are asking, it's going to be non-spontaneous. So that means delta G should be positive. And under what circumstances do you think this delta Z is going to be positive? When delta H is positive and delta S is negative. So under these circumstances, when the change in the enthalpy is positive and the change in the entropy is negative, so this term will become positive anyways. And if you have the two positive terms in this equation, the delta is always going to be positive, and in that case it's going to be non-spontaneous. So the correct option is going to be delta H A positive, fine, and delta S is B negative. So the correct option is going to be 1. Another question from the biochemical thermodynamics. It's given the anaerobic conversion of sucrose to lactic acid is given in the equation 1, and the combustion of sucrose is given in the equation 2. They have asked you to calculate the standard reaction enthalpy for each reaction using the following enthalpy of formation data. So all these enthalpy of formation for a particular component, for a particular molecule is given. So you have to use these values and then need to calculate. So if I have to calculate it for the first, reaction 1, I'm writing, calculate the standard reaction enthalpy. It's going to be summation of change in the enthalpy of formation for products minus summation of change in the enthalpy of formation for the reactants. Don't forget to take this stoichiometry here. You can denote it by N or M. That means these values, the moles and all. So let me calculate for the first reaction, what is this value going to be? Seems all right. All these reactions seems to be balanced. So that you can see by counting the number of carbon or the hydrogen or the oxygen. To me, it seems all right. Both the two equations seems to be balanced. Now, what I need to do, these are the products of 4 into what is the enthalpy of formation of for this lactic acid, which is minus 2,222. That's fine, which is going to be equivalent to the products, and then minus summation of reactants C12H22O11. It's a sucrose. I think I made a mistake here. So this value is not for the lactic acid. The value for the lactic acid is minus 698 kilojoule. Make sure these values are in the same unit, kilojoule, 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 kilojoule. And then for the sucrose, it's going to be minus 2,222 plus, I have to sum up these two values for the water. What is the value enthalpy of formation for the water given? It's given minus 289. Minus 289. Do some calculations. So 4 into minus 698, it's going to be minus 27. You can use the calculator. It's going to be minus 2792. This is going to be minus 2511, which is minus 2792 plus 2511. And the value is going to be minus 281 kilojoule per mole. Delta H reaction minus 281 kilojoule per mole this seems to be okay. Now I need to calculate it for the second. And yeah, you can calculate via this way, which is going to be I will just rub it. Going to be 11 H2O, enthalpy of formation of the H2O minus 289 plus the enthalpy of formation for the product. So the products are H2 and CO2. What is the value for the CO2 given? minus 393.5. So these are for the products. And then what is the values for given for the reactants? We are going to consider the enthalpy of formation for this O2 as a 0, because we all know that the standard enthalpy of formation for these elements are 0. And so what I need to consider the enthalpy of formation for this O2 as 0. It's a common thing. We all know that there is no change in the heat while forming this molecule. They are in their pure elemental state. So what I need to consider here only for the C12H22O11, which is minus 2222. So calculate it and you will get minus 5679 kilojoule per mole. Yeah, so the correct answer is going to be 3. Next, it's an interesting question where they have given the health risk of accidental exposure to a toxic heavy metal such as lead, mercury. So these are the occupational diseases where the people who work in these industries, they are more exposed to these heavy metals like lead, mercury, or cadmium, maybe reduced through treatment with a chelating agent. We all know that chelating agent traps the metal ions, which binds to the metal ions and form a complex that can be eliminated from the body. Now, these are the two of the molecules which they have given, the chelating agent, methylamine, CH3NH2, and ethyl-diamine, chelate cadmium as shown in the following reactions. Now, they have asked you to calculate the temperature range over which the chemical reactions 1 and 2 are spontaneous. So, again, we need to consider this Gibbs free energy equation, delta G equal to delta H minus T delta S. Now, the simplest thing is to understand, like, just by looking at these values, can I tell, like, under what conditions these are going to be spontaneous or not? Qualitatively, can I just have a look at these values? No. Focus in the second case. In the second chemical reaction, the delta H is negative and the delta S is positive. Now, under such cases, I mean, you are always going to find delta G negative. You are always going to find delta G negative. Why? Because delta H is given minus and the delta S is in the value is given plus 3.15, and you will just try to play with this equation. You will find this minus, this term is always going to be negative. Is this equation giving me some hint that this particular reaction is going to be spontaneous at all temperatures? By looking at these values, I can say that, like, I mean, this is going to be spontaneous. This is going to happen at all temperature. This particular reaction I'm talking about, cadmium 2, which is a metal ion, combining with this chelating agent to form this complex, and this reaction is going to happen at all the temperatures. Particularly, they are going to be spontaneous at all the temperatures. And what about the reaction 1? So if you look at the reaction 1, delta H is negative, fine. And then again, the problem is the delta S is also negative. I'm talking about, like, qualitatively. So under what conditions this reaction is going to be spontaneous? A bit at lower temperature, because at lower temperature, this delta H value is going to be, for a reaction to be spontaneous, I'm saying, if I have to make this reaction spontaneous, this reaction should take place at lower temperatures, which you can easily figure it out. When I'm saying spontaneous, I need to make sure that delta G is negative. And for that to happen, I need to make sure that if delta H is given negative and delta S is also given negative, also you need to sometimes have a look at these values. How big are these values? For example, I mean, the units are, all the units are same. Remember, the delta H is given in the kilocalorie, while the entropy is given in the calorie. So, I mean, I have some idea that this second reaction is going to be spontaneous at all temperature. This doesn't hold true for the first one. So I need to calculate at what temperature particularly the first reaction is going to be spontaneous. We all know from the Gibbs free equation, Gibbs free energy equation, that I can consider delta G as 0 under equilibrium conditions, and that will make my equation simpler. Delta H equal to T delta S. Under that condition, I can calculate temperature as delta H by delta S. So delta H by delta S equal to temperature. We will calculate it for the first one, minus 7.03 kilocalorie. Minus 7.03 kilocalorie. I will convert it into the calorie. Delta has given minus 2.58 calorie. What is the temperature going to be? We can use the calculator and you will find the value temperature equal to 2724.80 Kelvin, which you can consider it as 2725. I mean, we can even look at the options. What are the options given? 2725 for the reaction one. Yeah, so the reaction for this particular case, the reaction is going to be spontaneous up to 2725 Kelvin. If we'll increase the temperature beyond that, that is going to be non-spontaneous. The reaction will not take place. So I have to make sure that for the reaction one, I need to keep the temperature up to or below the 2725 Kelvin, which is, if we'll try to convert it into degrees Celsius, it's close to 2451.85 degree Celsius. So it's given in Kelvin. Reaction one is spontaneous up to 2725 Kelvin. Seems correct. Reaction one is spontaneous 3 Kelvin. Wrong. Reaction 1 and 2 are non-spontaneous at all temperatures. Not at all. The 2 is always going to be spontaneous. Reaction 1 is spontaneous up to 2725 Kelvin. True. True. And reaction 2 is spontaneous at 2229. No. By looking at these values, I can tell you that this particular reaction is going to be spontaneous at all temperature. Both reaction 1 and 2 are spontaneous at all temperatures. False. So the correct option is going to be 1. So we need to understand, what does it tell you? It tells you that, I mean, it's better to take this chelating agent as a drug molecule rather than taking methylamine, because this is the one which is going to work at all the temperatures, and we need to understand that our body have certain system which works well at 37 degree Celsius. So this reaction will be more feasible, more spontaneous at all the temperatures. Now, this is another question where they have asked, salts like sodium chloride are soluble in water because of. Simple. We all know that. Let's take an example of, I mean, they have asked sodium chloride only. So sodium chloride, the bond between them is the ionic. What happens when we dissolve it in water? There is a creation of the hydration cell, which results in the dissociation of the sodium chloride. So you have Na plus ion, you have Cl minus ion, and we all know that water is a universal solvent. It's having a dipole moment. It's a polar molecule. So what is going to happen? If you look at the structure of the H2O molecule, the two hydrogens are attached to a electronegative oxygen atom. Remember, because of the uneven distribution, or rather because of the electronegativity of the oxygen atoms, it can result in the generation of a partial negative charge at the oxygen and partial positive charge at hydrogen. So they are going to, like these water molecules, they are going to create a hydration cell. When I say hydration cell, they are going to orient themselves in such a fashion where oxygen lies close to the Na plus, and that results in the stabilization of these generated ions. I mean, it's a simple thing. Why do you think something will get dissociated if that reaction is not feasible or possible? So it's already there in the, it's already there with the chlorine molecule by forming a ionic bond. If it has to get solubilized, it has to be dissociated, and those dissociated structures should be stabilized. And how are these getting stabilized? By the formation of these hydration cells, where the partial negative end of the oxygen is interacting with the sodium ions. What is going to happen here? I mean, the same thing in a reverse fashion. So here the hydrogen atoms are going to be in close contact, because those are the ones which are carrying the partial positive charges. Sorry. And the oxygen away, because we all know that oppositely charged species attract each other. So salts like sodium chloride are soluble in water because of, this is the dipole, water is a dipole, this is the ion. So the correct answer is going to be ion dipole interactions. Where is that option? Not dipole. Hydrogen bonding, not dipole induced dipole. No, it's ion dipole. I mean, ion dipole is going to be the perfect answer. Remember, not electrostatic interactions. When we talk about like this water molecule is, remember, there is a difference between the partial negative charge and the completely charged species. So the electrostatic interactions, if I have to say so, or the ionic bond, they always prefer which are completely charged species, like plus, minus. When I talk about the dipoles, I need to represent those dipoles in a form of partial delta, in a symbol of delta, showing partial positive charges or partial negative charges. So the correct answer is going to be ion dipole. Remember, this negatively charged on this oxygen molecule in case of the water is not completely negative. Next question. Which one of the following combination of amino acids would show cation pi interactions? Again, very simple from the name. I mean, it's a link given where you can look at the structure of the amino acids for solving this question. So as very clear from the name, if I have to look at the cation pi interactions, I need to look for some of those amino acids which carry positively charged at the physiological pH. And what are those amino acids? Simple. It's lysine, arginine. I'm talking about the physiological system. Although they have not mentioned about the pH, but anyways, these are the ones which are going to carry positively charged in their side chain at a physiological pH. How about the pi? Now the pi, I'm going to get it from the aromatic amino acids. So much hint given. So what I need to do, I need to look for aromatic first. Arginine, alanine, these are the cations, fine. Cations, so I can see cations everywhere. From where would I get the cation? Sorry, these are the cations. From where would I get the pi? Like those are the pi electrons I'm going to get from the double bond which are there in the aromatic amino acids. Seems the tryptophan and the lysine is the correct answer. I hope you all know these structures. If I have to draw the structure of the lysine, I'm drawing it at the physiological pH, CH2, 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 one more CH2, and then 3M plus. For the tryptophan, as said, it's an aromatic amino acids. The ring is called as, the entire ring is called as the indole ring. I hope I'm not making any mistake while drawing these structures. I'm talking about these interactions, right? Cation pi interactions. So you will find some sort of interactions between these, which helps in the stabilization of the three-dimensional structure of the protein molecule. How about the proline? Remember, proline is an unusual amino acid, and of course, it's not an aromatic. If you look at the structure, it's a rather cyclic amino acid. So if I have to draw the structure of the proline, it's going to be Look at this structure. I mean, there are no double bonds. There are no double bonds. So this is the one. And remember, its backbone is involved in its cyclic structure. So this is for the proline, same like arginine. Valine is a not an aromatic amino acid. It's a simple hydrophobic or the non-polar amino acids, and its structure is CHCO minus S3N plus CH 1 2 1 2 3. I hope I'm minting the valency. So again, you'll not find any pi electrons here. How about the arginine? Arginine is similar to the lysine in nature. I'm talking about in it you will get the cationic form. So arginine has a structure COO minus CH. I should have rather written S3N here, depending upon the notation. S3N plus. Always remember the S3N for the usual notation is written on the left hand side, the CO minus on the right hand side. But anyway, then CS3, 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 and then NH. NH. And then C double bond NH. And here NH2. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. Seems all right. I'm just confirming it. Yeah. So this is for the arginine. So you'll get a positively charged here. You'll get some positive charge, which is going to act as a cation, like in these cases. But you'll not find the pi bonds from these amino acids. So the correct answer is going to be lysine and tryptophan. Another question on the biochemical thermodynamics. In biological cells that have plentiful supply of O2, glucose is oxidized completely to CO2 and H2O. Muscle cells may be deprived of oxygen during vigorous exercise. Good question. And in that case, one molecule of glucose is converted to 2 molecules of lactic acid, as represented by this equation, represented by 2 molecules of lactic acid. Where is the lactic acid lying? Sorry, this one. They're talking about this one. Glucose getting converted into 2 molecules of lactic acid by the process of glycolysis. It's a simple biochemical reaction which keeps on happening inside the cells. Given the thermochemical equations for the combustions of glucose and lactic acid, so they have given you the values for some of these chemical reactions, and you need to calculate the standard enthalpy for glycolysis. For this particular reaction, where 1 molecule of glucose is getting converted to 2 molecules of lactic acid. This seems to be balanced. These again, all these equations are balanced. Then the standard enthalpy of formation given for these reactions. But you need to be a bit careful here. Why? Because look at the direction of the reactions. The lactic acid should be there on the product side. Here the lactic acid is given on the reactant side. So I need to reverse this reaction, and by doing so, this is going, the value that the standard enthalpy of formation is going to be plus 1340. And also I need to, if you look at this particular, the final one for which I have to calculate the standard enthalpy for glycolysis, there are 2 molecules of lactic acid. So then I need to multiply this reaction with 2. So we are going to have 2680 kilojoule for this reaction. And then, so what I'm trying to say, you just write equation 1, 6CO2 plus 6H2O, and then reverse the below one, 3CO2 plus 3H2O, giving you 3O2. Rather 6 because I'm multiplying with 2, 6 CO2, 6 H2O, 6 O2, and 2 moles of lactic acid. I'm just writing CH3CHOH, COOH. Add these two values. So this will get eliminated. I can cancel these ones. I can cancel this one. And now the final equation which I'm going to get, C6H12O6, giving me 2 molecules of CS3, CHOH, COOH. So what I need to do, minus 2810, which is the value for this chemical reaction, plus 2680. And the value which we are going to get is 2810 minus 2680. It's going to be minus 130 kilojoule. No, not plus, minus 130 kilojoule. Remember, if I have to convert it into joule, it's going to be minus 130 into 10 raised to the power 3 joule. I hope all these questions are clear to each and every one of you. If not, feel free to comment. If you do have any question related to or any doubts related to these questions, please let me know in